When we talk about acids and bases, a very common term comes up, and that term is pH. Lowercase p, capital H. What does that mean? Well, for starters, no one's exactly certain what the P is supposed to stand for. This was a shorthand naming convention that a scientist used in his journals that were discovered later. And no one really knows why he was using P in front of it. The thought is that it's meant to be power of hydrogen, which was kind of a naming convention at the time, but no one's exactly certain. However, it's such a convenient way to look at acids and bases that it just stuck and we use it. So pH is going to be a very useful shorthand way to look at the concentration of an acid. And in order to understand what it really refers to, first we need to look at water, pure water. Pure water is H2O, right? So I've got H2O. And that H2O can sit in a beaker. Let's just draw this out, like a beaker like this. Nice large beaker. And I can have oxygen sitting along with hydrogen. There's my H2O. And it's going to be surrounded by other water molecules. And they're going to arrange themselves according to hydrogen bonding. Remember that hydrogen bonding is going to be this not intermolecular force, not inside the molecule, but outside. So it's going to have this preference for lining up its hydrogen with the oxygen on the other water molecule. Remembering that one side of this water molecule is negative and the other side is positive. So we've got positive here, we've got negative here. We've got positive here and negative here. So that's all well and good. But sometimes what happens is these get so close that this hydrogen bond becomes greater than this covalent bond. And this water molecule will steal this hydrogen from this one. And if that happens, then what we get instead is an oxygen that is bonded to 3 hydrogens. And we get another water molecule that's only bonded to 1. Now, when this happens, it's able to happen because, remember, those protons are so super tiny, and water, in this water molecule, the oxygen is so much more electronegative than the hydrogen that it is holding most of the electrons close to itself. So it would really look like I've got an oxygen here, I've got hydrogen here, hydrogen here. If I were to draw this electron cloud, it would really look kind of more like this. It would barely be touching these hydrogens. And so really on the outside of this water molecule, I've got just a tiny little proton just hanging out. So when this other water molecule takes this proton right here, it's going to just take the proton and leave all the electrons on their own. And so this whole thing, it was neutral as water, but now it's added a proton, so it's got a +1 charge. And this whole thing now just lost a proton and has a -1 charge. So this is our hydronium cation, and this is our hydroxide anion. This naturally happens in water. And so I can write out the dissociation of water as H2O, I should really put a 2 here, becomes H3O plus and OH minus. So 2 water molecules interact and become a hydronium and a hydroxide ions. How common is this? Because after all, if we really think about it, they'll split up, but then shortly thereafter, and look at this, this is a negative, this is a positive, those are going to want to come close together, and if this hydrogen right here, if this one gets too close to that oxygen, they will remerge and I'll have 2 water molecules again. So this really isn't a single reaction. It doesn't just proceed this way, it also goes back this way. So they're constantly, in any bottle of water, in any substantial amount of water, I've got water molecules interacting, reforming and forming and reforming hydronium and hydroxide, and then going back to water, going back and forth between these two all the time. And it's happening at a fairly constant rate, that results in it being about 0. That's not showing up very well. 0.000000001 molarity. In 1 liter of water, about 0.00006 zeros right here, 1 moles. So if I write this out in scientific notation, I get 10 to the negative 7 moles per liter. That's the concentration of these hydronium ions. And so when we say pH, what we're saying is how many H pluses, what is the concentration of H pluses in a solution? That's what pH is really referring to. It's a shorthand for looking at this. When we say H plus, what we're really saying is how many hydronium ions are there in this? Because what we really care about, what's really getting traded, yes, is this H plus, that is just the proton. But it's never just going to sit around on its own. It's always going to interact with something and get plucked off. And what's going to be most common in any aqueous environment is that it's going to get plucked off by a water molecule. So when we say pH, remember, we are looking at the concentration, this is how we write concentrations, of hydrogen. But what's really happening is we're getting a concentration of H3O. At the same time, we're going to have some kind of balance with the concentration of hydroxide. So if we go back to our examples of hydrochloric acid and sodium hydroxide that we were looking at yesterday, then HCl gets added into a beaker that's already full of a bunch of water molecules. And when that happens, if I add a substantial amount of hydrochloric acid, then what's really going to happen is it's going to break up. Let's draw another beaker. I'm going to have H plus here, Cl minus here, and this H plus is going to get plucked up quickly, instantly, by a water molecule. So it's going to grab it there, and then what I'm really going to have is H3O plus H3O plus C minus. So I'm going to have the natural H3O pluses that get made just by water, just existing. But I'm also going to have added all of the extra hydronium that I got from adding HCl. So that's going to boost the concentration. So if my natural concentration was 10 to the negative 7th in just regular water, I might have boosted this concentration. I might have made it 10 times more to 10 to the negative 6, depending on how much of this I added. So we're going to look at how to get pH from these numbers shortly. But for now, what we're really saying is that as I add in these guys, I am boosting the concentration. I'm boosting the concentration of my H3O plus. But what happens to the hydroxide ions? Well, remember, we've got those floating around in here too. So let me just draw one of those. Suddenly, these hydroxide anions are being vastly outnumbered. And so the concentration of hydroxide is going to go down. And it's actually going to go down proportionally to how much the hydronium concentration goes up. So if this went up 10 times, then the hydroxide concentration is actually going to go down 10 times. So if this started at 10 to the negative 7th, it's going to go down to 10 to the negative 8. That's how these are going to start to look. So next, we need to be able to figure out how to calculate the pH from a concentration like this in scientific notation. And it's actually very straightforward once you know the simple math concept behind it. So we're going to cover that next.